All right, well, good evening and welcome to lecture 6 of MT225. Uh, Last week, we focused on working with vectors and dealing with vector addition. This week, we're going to see how that skill is applied in solving practical problems. So we'll start off relatively easy, but these kinds of problems can get somewhat complex and they form really the basis of every problem that we solve throughout most of the rest of the semester. So we continue building up our skills and our complexity on the problems we can solve. Let's see. Contact information for the class. We've got all that there. Hopefully, everyone is familiar with that by now. A little bit of news on a possible room we may be able to get into at the earliest on Wednesday. I just have to make sure I've got access to it and such. But I will email the class tomorrow if if we have access to a room. If we don't, then if you don't hear anything from me, assume that we're online Wednesday night. So unless otherwise specified, we're online. Let's see here. Homework 1 was returned. If you didn't get email with your grade breakdown for homework 1, make sure you let me know at some point. I sent those all out on Saturday. So you should have gotten something back. Everyone who submitted an assignment got something back on that. As far as comments, returning the homework kind of the way I did is really useful for being able to write up a little bit more extensive comments than I normally would on the paper. A couple recurring themes that came up. People were a little bit aggressive rounding. Uh, all of these were math problems. There were no measurements involved specifically, so there was no real idea of how many significant figures you should keep. And when that's the case, it's always better to keep more sig figs than it is to keep fewer. Generally, that rule that we followed in the first semester in the A&P program will work for you. I keep 4 to 5 significant figures, and you'll generally be safe for most of what we do. As we get into more practical problems starting tonight, there will be some aspect of the problem that will tell us about how many significant figures we need to keep. So in a more realistic situation, it's a little easier to figure it out. In a situation where it's not easy to figure out, in most situations, I will tell you round to a certain number of sig figs. And we'll see what that implies in problems that we work on tonight. So homework 1 came back. Otherwise, performance was just fine on that. Couple math errors here and there. Couple simple mistakes people made and such. But as you get a little bit more practice doing these kinds of homework assignments compared to what you're used to in 225, you'll be able to in the A&P program, you'll be able to anticipate those kinds of problems and make sure you don't make those simple mistakes. Homework 2 has been issued. That is up on the website and has been since I think yesterday. So I posted that up there. So chances are you haven't had a chance to look at it yet. If you're a little bit ahead of the curve and have started to look at it, you'll have a chance to ask questions here in a moment. And then quiz 1. Actually, no, I did post that. I'm off by a day, so I posted that last Wednesday. So homework 2 has been out for a little while. It was the first quiz I posted yesterday afternoon. Quiz 1 has been posted, and that is due just before midnight tonight. So make sure you scan an email or send pictures on the results you have for that quiz by that deadline. I've gotten a couple submissions already. If you haven't gotten a chance to look at it yet, it's the kind of thing that I normally take care of in the last 10, 15 minutes of class when we're meeting in person. So it's not a huge time investment, especially if you've had a chance to go over your homework and make sure you are comfortable with any mistakes you might have made on those. So that is due tonight. Anyone have any questions on the homework? All right. Well, Wednesday night, you'll have a chance to ask for one of the questions to be worked out as a class example. And usually I have candidate questions already in mind. So chances are, as you work on it, you'll figure out which one is probably going to be best to try to work out in class. But for the most part, the problems will be pretty straightforward. But we'll get a little bit of practice on our uh, well, on the next application of problems here tonight, but that'll reinforce what is being worked on for the homework assignment uh, this week. So let's see here. Today we are taking a look at force systems. So we've looked at vectors. We've got our toolkit put together. We know what we have the tools we need to work on these problems. The vector that we're most often going to be working with is a force vector. And forces apply to objects and change their motion. We're going to be looking at systems specifically that are static, meaning that all of the forces cancel out. That's a very specific situation that we call equilibrium. And we're going to look at the generic force system today, how that's set up, and then we'll restrict it to just systems in equilibrium. And that will let us come up with equations that we can solve. Those equations are based on our vector sums that we did last week. So we'll look at a tool that helps us organize the forces that are acting on an object and clarify what those forces are, what we call a free body diagram. We'll see how to set up one of those. And then we'll look specifically at the idea of equilibrium and what that means with respect to the forces that must be acting on something. And we'll see how we can use that to create equations that we can solve and help us learn things we didn't know about a system before we started. And in our practicum session tonight, we'll be working on equilibrium problems. I'll put together a couple equilibrium problems for you to work out. And just like last week, we'll give you some time to work on those, and then I'll work out the solutions. So let's take a look at the basic ideas here with force systems. The first thing we have to get is a little bit of terminology. And the first piece of terminology that's going to be important to us is what we call the point of application of a force. A force's point of application is pretty much what it says. It is where the force is applied to the object. If you think about exerting a force on something, we tend to think about forces as what we call point forces. We like to imagine a single point on the object that we can connect that force to. Now, that's not always true. In fact, it's never really true. We can never really hook a force right on to, say, a single molecule or a single atom or something like that. What we deal with in reality are what we call distributed forces. But it's a lot simpler to think of point forces. So in all of our problems that we're looking at first, we'll be considering just point forces. And point forces are not a bad approximation in most situations. If you think about, for example, lifting something with an engine hoist. If you lift up an engine with an engine hoist, there's a hook that we're connecting to the engine. There's a lifting hook that connects at pretty close to a fairly small area on that engine. There's not a lot of area that force is spread out over. It's connected onto something that's pretty localized. So it's not a bad approximation to think of it as just a single force that's applied at a single point instead of some force that's spread out. So in most every situation, we're going to be able to identify where a force is applied, and that will be the point of application. We will look at distributed forces a little bit later. And the big goal there is to figure out how do we turn it into a point force, an equivalent point force. That's effectively what we do in weight and balance when we try to find the center of gravity of an aircraft. The weight is a distributed force. The center of gravity is the point of application of that weight force. It's where we can think of the weight as attaching to the object. Then we have closely associated with the force and the point of application is what we call the line of action. Now, this one might be new to you. A line of action is a straight line through the point of application in the direction of a force. In fact, it can be in both directions. Lines go in both directions. So let me illustrate what that looks like here. So let's say we have some object, and I'm just going to pick something that looks sort of like that. It's some potato. Why a potato? Well, it's easy to draw. So we've got this potato. I'm going to attach a force to it. I'm going to pick a point right here and say that is where I'm applying my force. So we can clearly see where the point of application is of that force. It's where the force is hooked on to the object. The line of action of that force goes essentially infinitely in both directions. So the line of action of a force is kind of a visual tool for us. We'll see that it has some important physical characteristics here and some physical consequences. But that line of action is a line extending in both directions, in the direction, have parallel essentially or along the force. So it's got the same directionality as the force in that it's lined up in the same direction, but it goes in both, it goes infinitely in both directions. That's the line of action. Lines of action will be very useful to us, especially as we get into a little more complex problems and have to bring in the idea of moment. Now, you're all familiar with moment as A&P students. You've all done weight and balance, so you know what moment is. And moment is going to play a pretty important role in the problems we're going to be dealing with next week. So for now, we can leave that out, but lines of action and moments will be very important to us soon. So that's the line of action. Then we have kind of a strange word. I only bring it in because this is in the course description and it's in the course outline. It's the word is coplanar. Coplanar means in a plane. It means two things share a plane. So when you've got a flat surface, if we have two vectors that lie in that flat surface, then they are coplanar. Essentially, what this is saying is that when we deal with a coplanar system, we can draw it out completely in two dimensions. We don't need a third dimension. So essentially, coplanar problems are problems where we only need two dimensions. So that's a simplification for this class. All the problems we deal with are going to be coplanar problems since we can't deal with a third dimension. We're not going to deal with problems that have a third dimension in this class. So that's coplanar. And then we have another word that may be new to you, concurrent. Concurrent normally means at the same time. Two events can be concurrent. In force systems, we look at concurrency as having to do with the lines of action of all the forces that act in the system. When all the forces that act in a system have their lines of action intersect at one point, we have a concurrent system. Concurrent systems are a lot simpler to work with than non-concurrent systems. Concurrent systems are what we're going to be looking at this week. Non-concurrent systems are what we'll start into next week. So let me show you the difference between a concurrent and a non-concurrent system. So we go back to our potato here. Here I just have one force. Maybe we'll label it F1. If I put another force on it, let's put a force that's pushing right there. So push or pull doesn't make any difference. It's still got a point of application. Call that F2. And then we're going to have a line of action. That line of action goes along the force through the point of application. So there's our line of action. Now the two lines of action from force 1 and force 2, they intersect at one point. So this is a concurrent system because all the forces that are acting in the system have their lines of action intersect at a single point. This is also a coplanar system because the two vectors that we've got are both in the same plane. I'd have a hard time drawing them on the piece of paper if they weren't in the same plane. So let's add a third force here. Let's say we've got attached up here F3. Well, F3's line of action is going to go through the same point. That makes this a concurrent system of forces. So all three of these forces, they live in the same plane, so it's a coplanar system, and all three lines of action intersect at a single point. That makes it a concurrent system. Well, if we had one more force in here, maybe we can have a force that spoils the concurrency in this system. If I have a force over here like this, that's attached right here, and I've got my force like that, well, the line of action of that force is out like that. It doesn't intersect with the other three lines of action at the same point. This would be a non-concurrent system. And in non-concurrent systems, we have a little bit different behavior than we do with concurrent systems. In a concurrent system, moment doesn't exist. Think about what you know about moments and you know about from weight and balance, forces times distances or forces times arms. When you applied a force right at the pivot point or right at the datum, you got no moment. Well, essentially, when we have a force pushing or pulling on this one point, if all the forces push or pull on that one point, they're not going to cause this to rotate. There's no tendency to make this rotate. You might be able to see that physically, that if all three of these forces are set up so that their lines of action go through a single point, there's not going to be a tendency for this to want to rotate. But as soon as we add a force in that's not concurrent, now we have the tendency for this to start to rotate. We have a moment. If this was our pivot point, if we had a nail through the wall holding this, or through this, holding it to the wall, this extra force here would cause it to try to rotate. It would have a moment about that point. The other forces don't have a moment about that point. So in a concurrent system, we don't have to worry about moment. Non-concurrent systems, we have to bring moment in. Now, normally I don't talk about moment this early, but all of you have dealt with moment before, so you have some idea of what it is. We'll formally introduce moment next Monday. So in a concurrent system, all the lines of action intersect at one point, and we have a simpler system to deal with. So let's take a look at another term that comes up fairly frequently, the difference between an internal force and an external force. External forces are forces that are applied to an object. Now, they may be applied because we're pushing or pulling on them. They might be applied because they have mass, so they're being attracted by the Earth. And all of our systems, for the most part, take place on Earth. So we've got some gravity, some weight we might have to worry about. Well, the forces are applied to that object, and those forces can change how that object moves. External forces are what are accounted for in Newton's second law. They contribute to acceleration of the object. When we push on something or pull on something, we're applying an external force to try to get it moving or to stop it moving, to change its motion. So external forces, in a certain sense, we have control over because we can apply those. we put loads on a system, and that creates the that is an external force that we're applying to that system. Internal forces, on the other hand, are what forces exist inside an object that keep it together. For our purposes, for this part of the course and for the first, really the first 2/3 of the course, we are focusing on external forces. When we get to the last part of the course and look at materials and strengths, stresses and strains and all of those are really all about internal forces. Internal forces you can think of as kind of being the strength of the bonds that hold the materials together, hold the molecules that make up the materials together. Those are internal forces. They hold an object together. We're going to assume those internal forces are as strong as they'd ever need to be to handle whatever external forces we'll put on the objects. In reality, there are limits, and we have to worry about those, or we end up with things that break, things that become overloaded. For our purposes, at least until we start talking about the strength of materials, all the materials we'll use have infinite properties. We can put as much force on them as we want because they have an infinite capability for internal force. So internal forces are just structural internally to the object. They hold the object together. They keep it from breaking or changing shape. Internal forces do not contribute to acceleration. It's only external forces that change the motion of an object. And one last piece of information that's pretty useful to us, a little bit of simplification on how we draw out how forces are applied to an object. We have what we call the principle of transmissibility, which is basically a fancy way of saying that you can put a force anywhere along its line of action and the physics won't change. The motion of the object won't change. As long as you move that force so it doesn't change its angle, it stays on its line of action, and you don't change how much force is involved. So that helps us to simplify how we draw our force diagrams and our free body diagrams. For example, it's a lot easier to draw all of our systems as if all of our forces are pulling on an object. That's not always the case. We've got push forces, compressive forces involved. It's a lot easier to draw that as a pulling force. It helps us to get the angles worked out properly and to visualize the system better. The principle of transmissibility is just acknowledging that we can move those forces around as long as we keep them along the line of action. So we'll take a look at a couple examples of that just to get the basic idea down. First, let's look at our potato here. If we look at force 1, well, force 1, I can move anywhere I want along its line of action, and it won't change how this potato moves. So if I move force 1, I could move it down here so that force 1 is applied directly to that intersection point. I could do the same thing with force 3. I could move it down here so that it's applied right off of that intersection point. And I could take force 2 and I could pick it up and move it down. So instead of pushing, it's more of a pull. As long as it's along the line of action, so this would be F2, F1, and F3. As long as it's along the line of action, we can put that force anywhere we want. And in a concurrent system, there's always a special point, that point where all those lines of action intersect. So that's the point we want to move all the forces to. And in many problems, that's natural. That happens to be a physical point where things are tied together. It doesn't have to be, but it doesn't have to be a physical point, but that point does exist, and it's always a simplification to move the forces so they pull on that intersection point. Now, another example would be to look at a weight sitting on a beam. Now, a beam could be something like an I-beam or maybe a 2x4 on its side, something like that. That's a simple depiction of a beam. If I put a weight on that beam, let's say we put a 100-pound weight. Schematically, I could represent the force of that weight on the beam by redrawing the beam. And instead of looking at the box symbolizing the weight, I could replace the weight with a force equal to 100 pounds, labeled with a magnitude of 100 pounds. Now that force pushing down on the beam, that's going to create all sorts of internal forces, and other forces that we'll learn about called reaction forces will happen as a result of applying that force. It doesn't matter to the physics whether or not this is pushing on the beam or if it's pulling on the beam. Let me redraw it. If I redraw it here and use the principle of transmissibility to pick up this force and move it down, so instead of pushing on the top of the beam, it's pulling on the bottom of the beam. What I've done is I've moved the force along its line of action. So I could draw this as a pull down with 100 pounds of force or a push down of 100 pounds of force. Nothing would change inside the beam. The beam doesn't care whether it's pushed on or pulled on in this case. So the forces that are inside that beam that are created as a result would be the same. The way that we support the beam would feel the same forces. The blocks we might have this sitting on down here, those would feel the same forces, whether there's 100 pounds pushing down on the beam or 100 pounds pulling down on the beam. So that gives us a tool to help us simplify our drawings. We can move our forces around along their lines of action in the same direction. As long as we don't change the direction of the force, as long as we don't change how much force there is, the physics won't change. So that lets us simplify things quite a bit. So that's a little bit of terminology. Let's see how we can apply it in looking at a free body diagram. So let's go to a similar picture of what we just looked at here, a weight sitting on something. So I'm going to draw just a schematic picture here of some box sitting on a table, and I'll show you what that looks like here in a moment. The idea behind a free body diagram is to recognize that we often have lots of different components that are acting together, that are interacting with each other. In the previous example, the example with the box on the beam, we had two pieces. We had the box and we had the beam. We have to be clear, what is the object we're looking at? What is the object of interest here? Are we studying the beam or are we studying the box? Which is the important part? The free body diagram lets us isolate the object that we're looking at, the object that we're interested in studying, and eliminate all the other objects. We can replace all those other objects with the forces they exert on the object we're interested in. And I'll show you a quick and easy way to figure out whether or not there are forces on an object when we draw our free body diagram. So the idea here is to isolate a system by removing it from its support mechanisms. Those supports might be something like a table. It could be blocks. It could be chains or ropes that are tying something to a ceiling structure. Could be bridge abutments. Could be all sorts of other support systems that are important, but that we're really not directly interested in. All we really care about from them is what force they apply on the object we're interested in. So we remove supports. When we draw a free body diagram, we remove the supports schematically. We don't do this physically. We don't want to remove the supports physically and then have everything crash down. We have to remove those supports schematically and replace them with the forces they supply. That gives the object an appearance of just sort of floating out there in space with a bunch of arrows pointing at it or pulling on it, pushing on it. That's why we call it a free body, because it's floating out there just connected to these forces. So let's go to our picture here. Here's a box sitting on a table, and a rather crudely drawn table, I admit, but we'll deal with it, I suppose. So we have really two objects here. We can in fact think of a whole bunch of different objects here because we got this thing sitting on a floor. So we've got the floor, which might be part of a house, for example. So it's got beams and it's got uh, maybe some underlayment, something. It's got a bunch of different pieces to it. We've got this table, and then we've got this box. In order to analyze a system, in order to figure out what's going on with it, we have to decide what our system is. So we have to pick one of these to be our system. And most often, it's going to be whatever object is sitting on top of some structure, some support. And usually it's clear from the problem what it is, what the object of interest is. In this case, it's the 100-pound force. So we need to figure out what are the forces acting on this 100-pound box. The easiest way to lock down the forces that are exerted on a box or on any other object by contact is by drawing a little kind of bubble around that object. When we draw a bubble around that object, we call that bubble a system boundary. Essentially, it divides the universe into space that is inside and space that is outside. Once you draw a boundary, you're essentially splitting things in two. You are looking at what's inside and what's outside. Well, if we take that system boundary, that bubble, and we shrink it down as far as we can, certainly if we made that bubble big enough, it could include the table, it could include the house, it could include the planet. We want the smallest bubble that we can get. So we shrink that bubble down until it just includes the object that we're interested in. Anything that we can't get rid of, anything that must cross that boundary or touch that boundary, has to be represented by a force. So if we go off to the side here and we draw our 100-pound box, if I want to get rid of this table, I've got to represent the force that this table is exerting on this box by drawing an arrow. And that force is an upward force. The table has to push upward on the box, otherwise the box would fall to the ground. So we have a force due to the table on the box pushing up. Now, how much force that is, we don't know yet, but there is a force there. We've removed the table. The table's gone, but we've replaced it with a force, with the force that it supplied. So we've simplified the system quite a bit by eliminating a lot. All of this support, the table, the house that table's sitting on, the foundation that house is sitting on, the planet, and so on. We've eliminated all of that and replaced it all with just this one force. That's the advantage of the free body diagram. The free body diagram lets us simplify the picture so that we can better see what is acting on the object that we're interested in. Let me show another example here where we have a few, let's say we've got a few ropes hanging on an object. So here we've got this beam. Maybe we'll tie a rope to the ceiling over here. Maybe we'll tie something to the wall over here. This little symbol with a line and the little slants drawn off of it is kind of the universal symbol for some sort of structural anchor. So this could be some sort of wall that's got a fitting installed on it that I could tie that rope to. Maybe we have a box sitting on top of that 100-pound box. So we've got this system we've got this beam, and we've got this box, and we've got these ropes. We've got the ceiling, and we've got the wall, and all that structure there. If we want to draw a free body diagram here, if we drew a free body diagram of the box, it'd look pretty much the same as what we already drew. In a system like this, which is a system we'll learn how to work with next week, in a system like this, we draw the free body diagram of the beam. And the way we isolate that is to draw our system boundary around the beam. And that'll divide the universe into what touches the beam or what is near the beam and everything else. So when we draw our free body diagram of the beam, we can draw the beam down here. We always keep the object that's inside the bubble. Everything else is what disappears. Anything that crosses that system boundary or touches that system boundary has to be represented by a force. So if we look at what had to cross the boundary, we've got this force up here, this chain or this rope, and we can make a reasonable guess about what direction that is in and whether it's a push or a pull. Rope can only pull on things. So we've got a force that looks like that. Maybe we call that F1. We've got our weight, which is pushing down on the beam. We could replace that with a force of 100 pounds there. And then we've got this other rope that's attached to the wall. That crosses the system boundary, so we'd have to replace it with a force. Maybe we'd call that F2. And one of the things we'll learn how to do next week, with enough information, with enough angles and geometry, size and shape of things, we can come up with some equations to figure out what F1 and F2 have to be to make sure this is going to be in equilibrium, this is going to be in balance, that it's not going to move. That's where we're headed with it. That's the free body diagram of the beam. Anything that crosses the boundary or touches the boundary has to be represented by a force. Now, there's one exception. There's something that's often hidden that you can't see touching the boundary or crossing the boundary. Let's go back to our simple box on the table here. That box is labeled with 100 pounds. That means that it weighs 100 pounds. And if you think about what weight is, remember this for the FAA, weight is the force of attraction between the earth and an object. We can't see gravity crossing the system boundary, but it's there. Anytime an object has weight or mass, there's going to be an attractive force between that object and the earth. Now, in some problems, we'll eliminate it. In some problems, we won't worry about it. In most beam problems, for example, when we're dealing with a beam, those beams are, although you think of them as being pretty heavy, think about a steel I-beam or something like that, they don't weigh nearly as much as the loads we tend to put on them. So if we've got a 200-pound beam, but we're putting 50,000 pounds of force on it, that 200 pounds really doesn't make a whole lot of difference. So oftentimes we consider the beams to be weightless to simplify things, but in other situations we can't eliminate it. So for example, this 100 pounds, when we draw the free body diagram of this box, it's got to have another force pulling down on it. It's got to have gravity. It's got to have weight pulling down. So there are two forces acting on this box. There's a force due to the table pushing up on the box, and there's a force due to gravity pulling the box down. In our beam problem, if we decided that it's a bad approximation to exclude the weight of the beam, then we have to take into account that this beam has some weight to it. That weight is always applied at the center of gravity, and there'd be some amount of weight pulling down. We'd have to know what that is. We'd have to have some information about that beam to be able to figure out what its weight is. So weight can be a little bit tricky in a free body diagram because you can't see it. So you have to take it into account by hand, essentially. Everything else you can see. When you draw that bubble around the system, anything it cuts, anything that touches it has to be included in the free body diagram. So that's the basic idea behind the free body diagram. Any questions so far? All right, so let's go back to the screen here. There we are. So free body diagrams, the reason we do a free body diagram is because it helps us to isolate what is actually acting on the body, on the object that we're interested in. It helps us to make sure we catch all the forces. Because if you leave a force out of your picture, if you're trying to analyze a system, remember these are all physical, real systems. These are things we can go out or build. These may have been things that are already built, and we're trying to make sure they're safe, make sure that the forces aren't incorrect or aren't too much for the materials. So if you miss a force, if you forget a force, your math is not going to really have any bearing on reality or connection to reality. So we want to make sure we catch everything. We want to make sure our model on the page matches reality to within a reasonable amount. There's always going to be approximations. There are always things that we're going to assume are small or are big that can be eliminated or must not be eliminated. But we want it to be a reasonably accurate representation of the real system. So we use free body diagrams as a tool to make sure we've caught all the forces. And about the biggest problem I see with beginning students in this area is forgetting forces, losing a force. You lose a force, and all your answers are going to come out wrong. So let's see. We've done a couple examples of free body diagrams. One of the classic ones that we'll be spending a good bit of time with, and one that we'll work on tonight as an example, is a weight suspended from a wire. So the weight suspended from a wire looks something like this. We've got some sort of ceiling, and we want to hang an object from it. Say we're getting everything decorated in the new hangar, and we hoist up the Irma D so that it's strung up to the rafters in the new hangar. Well, we wouldn't want to use just one rope for that. We'd probably want to use at least two. So we've got some object. It's going to weigh something. We usually write what it weighs on it. Maybe it's 2,400 pounds or so. And then we've got a wire that runs to some attaching point and makes some sort of connection to the ceiling. So we've got some fittings here. We've got some connection where that wire is attached to something that maybe is hooked up to the load. Now, oftentimes in these kinds of problems, we're interested in determining how much force is on each of these wires. How much force is on that can be important, because if the wire is too small, then it might not be able to handle the amount of force we're putting on it. And it could snap, and then fairly heavy load starts falling down. Gravity wins, and we have a dynamic situation. We want everything to be static. We want everything to be stationary. So we have to be careful about our free body diagram. Your first instinct might be, especially if you've gone through some physics class or something like that in the past, your first instinct might be to try to draw the free body diagram of this weight. But if you do that, you're not going to expose the forces in these wires. You're going to free body diagram that looks something like this. You've got 2,400 pounds pulling down, and then because the system boundary cuts through this rope that's attached to it, you'll get some amount of force pulling up. You don't necessarily know how much force, but you'd get some amount of force there. That doesn't give us any information about what's going on in these two ropes. So there might be a better place or a better object to choose as our system. And in these kinds of problems, the system is really the point where all of those ropes connect. It's right where where the two or the three wires connect together. If we draw the free body diagram of that point, there's that point right there. We cut through 1, 2, 3 ropes or 3 wires. So there's got to be a force due to this wire right here pulling down. So maybe we'd call that F1. There's a force pulling up and to the right. Maybe we'd call that F2. And then there's a force pulling up and to the left. And that might be at a different angle. So we call that F3. There's our free body diagram of the connection point between those 3 ropes or 3 wires. Now, if you think about it a little bit, we know what F1 is, because the only way that this can pull down is if it's transmitting the weight. Essentially, gravity's pulling down on this 2,400 pound load. Something's got to be pulling opposite that to keep it in equilibrium, to keep it balanced. So you'd be correct in assuming that there's 2,400 pounds of force pulling down on that point. That's gravity pulling down on the box. The other two, we need some more information for. We need some information about angles or about the lengths of these and the sizes to be able to figure out what those angles would be. So we can't solve that problem right away here. We'll see a version of that tonight that we can solve. But that's another common setup for a free body diagram and how it can be useful to expose what we're interested in. In a sense, you can't figure out what you're interested in. You can't calculate what you're interested in unless your system boundary cuts through it. So there has to be something, or touches it. There has to be some way to expose in the free body diagram the unknown force that you're interested in figuring out. And the whole point of these problems is to figure out unknown forces, figure out how much force is applied in on some of these supporting mechanisms. So let's put this all together here and look at the idea of equilibrium. Now, you know from weight and balance, equilibrium is when all the forces and all the moments cancel out. Well, we're going to be dealing with concurrent force systems. So in a concurrent force system, we don't have any moments. So that means all the forces have to cancel out. A system in equilibrium doesn't accelerate. Essentially, it's Newton's first law. Newton's first law says that when the net force is 0, fancy way of saying all the forces cancel out, then the acceleration is 0. Acceleration being 0 doesn't necessarily mean that things are stationary, but it means they're not changing. Think about an airplane in straight and level flight. You've got lift opposing drag, or you've got lift opposing weight. You've got thrust opposing drag. All those forces are equal and opposite. So the sum of those forces, if we were to add them up, taking into account direction, essentially do the vector sum would be 0. So a system in equilibrium has a vector sum of forces that is 0. That system could be moving or it could be stationary. In our class, they will all be stationary. We're not interested in bridges that are going down the road at 30 miles an hour. We want the bridge to be stationary. So we're looking at static structures. That's what static means. It means that it is not moving. So we can go a step further with Newton's first law and say that for bodies in equilibrium, there is no motion. So in a concurrent coplanar force system, that system's going to be in equilibrium when the vector sum of forces vanishes. Vanishes is just a kind of a fancy math way of saying goes to 0. Makes me sound like a magician, I suppose. The vector sum vanishes. So it goes away. It goes to 0. That's the tool we're going to be able to use to come up with equations. Last week, we learned how to add vectors together to form a vector sum by breaking the forces up into their horizontal and vertical components, and then add up each piece. In application, we know what the sum needs to be. We know that when we add up all those x components or we add up all those y components, if that system is in equilibrium, that sum has to be 0. So since we know what the sum has to be, that leaves us with the possibility of solving for an unknown quantity. Each sum, the sum of forces in the x direction and the sum of forces in the y direction, the two components of each force, has to go to 0 in order for an object to be in equilibrium. So when we add our forces together, if we have an unknown force, then we have some missing information. But at least we know what the sum needs to be. We end up with two equations that we can solve and find that unknown force. So all of the systems we look at in this class will be in equilibrium, and that always means the sum of forces equals 0. The sum of all the x components when you add them all up, or the sum of all the y components when you add them all up, the vector sum equals 0. And that gives us our equations of equilibrium. So in a system, one or more of the forces is going to be unknown. So using the fact that the system's in equilibrium and that we know that the sum of forces has to be 0 in equilibrium, we can figure out the unknown forces. Now, we had two sums that we did last week. We added up the vectors in the x direction, or the x components of the vectors. We added up the y components. Our forces as vectors have x and y components. So we'll take a sum of forces in the x direction, and we'll take a sum of forces in the y direction. That's two equations total. Sum in the x direction and a sum in the y direction. That gives us the ability to handle two unknown quantities at most. Each equation buys us the ability to find one piece of information. So the only way we can solve an equilibrium problem is if we have at most two missing pieces of information. Now, what those two pieces of information are, they could be two forces, two magnitudes. They could be everything about a force. Remember that forces have two pieces of information built in. It could be the magnitude and the direction of that force. The most we can handle are two missing pieces. So at worst, the two equations that we get from our sum of forces in the x and the y direction, it'll always end up being a set of simultaneous equations. If we're lucky, and we are in most situations, fortunately, those two equations will be what we call decoupled. Those two equations won't be like what you saw in homework 1, where you had x plus y equals 3 and x minus y equals 7. There'll be two separate equations, x plus 3 equals 5 and y plus 10 equals 20. Two equations that we can solve separately from each other. In the worst case, we end up with simultaneous equations that are tied together, that we can't solve independently of each other. But we have the tools to do that. We know how to handle that when that situation comes up. And it will in certain situations. It will come up. And we'll do some examples of that probably on Wednesday. So at worst, we'll end up with a set of two equations in two unknowns. So let's try an example. Let's start with about the simplest example we possibly can so that we can work through the basic steps that are involved in solving a concurrent coplanar force system, and then we'll bring the difficulty up a little bit at a time. We should have enough time to get a couple examples in here before the end of the lecture section. Anyone have any questions before we get started? All right, so let's start here with let's go back to the box on a beam problem. And with the box on a beam, we have some beam sitting across maybe a couple concrete blocks sitting on the ground. And then we've got this block. And let's make that block weigh 50 pounds. And the block is going to be our system. We want to find out how hard is that beam pressing against the box. How much force is that beam exerting? So we'll draw our system boundary around our block. And because it's just a block, we could kind of shrink it down to a point. It doesn't really matter how big that block is physically. It's really just a single point where all the weight is concentrated. We can look at the center of gravity. So when we draw our free body diagram of this weight, we'll just draw it as a point. So it's a little nugget that weighs 50 pounds. Now there are two forces here. There's a force where the beam is touching the box. And you might be inclined at first to draw that as a force pushing up, because that's what it is physically. If you were the person supporting that, holding 50 pounds up, you'd be exerting an upward force. But we're going to use the principle of transmissibility here. Rather than drawing a force pushing up on that point, we can translate that through and instead draw that force as pulling up. It's a little clearer that way because all the tails of our vectors will end up at the same place. It can get confusing when there are heads and tails of vectors touching the same point. Now, something I should say before we go further to draw the free body diagram is we do have to define a coordinate system. We have to know what direction is horizontal, what direction is vertical, what's X and what's Y. And rather than drawing the whole big coordinate system that we drew last time when we were working with vectors, all we really need is a reminder of what direction is positive X and what direction is positive Y. And a lot of times we just do that by going over here someplace and drawing something that looks like this. Just a little tiny set of axes. The origin really doesn't matter in these problems, so all we really need to know is what direction is positive X and what direction is positive Y. And here we've got that. So horizontal to the right is positive X. That implies that to the left is negative X. Up is positive Y, so down will be negative Y. And that'll give me some information I'll be able to use here. I can translate that down into my free body diagram. So I've got my X and Y. So the first step in solving this problem is going to be to draw a free body diagram and define a coordinate system. Now, I don't know yet how much force this beam is pushing up on that 50-pound weight with, but I have a pretty good guess, but I'm just going to label this as an unknown. I'm going to label this as a force F. Now, that alone cannot be in equilibrium. Notice how there's no balancing force drawn yet in my free body diagram. I'm going to just erase that there. In my free body diagram here, I've only got one force. A force alone cannot be in equilibrium unless that force is zero. So there must be another force here. And part of the skill, the not so mathematical skill, but a little bit more physical and intuitive skill in working on problems like this, is to be able to look at a system and say, and be able to convince yourself this is in equilibrium, or maybe there's something missing, to be able to believe that this is going to be in equilibrium. Well, I can't believe this force alone would be acting in equilibrium. There's got to be something else, and the missing piece is gravity. There's weight here. This box is being pulled down by gravity, so I have to include that. There's a weight force right there, and that weight force is 50 pounds. Always helps to label the things you know. Don't get too involved in saying, well, I'm going to label that W, and then I'm going to define W as 50 pounds and do all that. Just label it right in the drawing. It'll make it a lot easier that way. So there's our free body diagram of that box. We shrunk the box down to a single point so that we can just look at its center of gravity. We have a force that we're drawing as an upward force, as a pull on the box, even though it's really a push. We transmitted it through along its line of action. And we've got weight. We've defined a coordinate system so we know what direction the forces are in. So that's the setup to the problem. The next step is to do a vector sum. We've got two vectors here. We want to add them together. And the only way we know how to add vectors together is to break up the components, break up the vectors into x and y components, and sum those x and y components together. So that'll be our next step. Our next step will be to break these two forces up into x and y components. So I'm going to label my unknown force, force 1, and I'm going to label this 50-pound force pulling down, force 2. And I can go off to the side here. I've got force 1 and force 2. Each one's going to have an x and a y component. And if you're already feeling comfortable with this from perhaps other work you've done, you might be thinking, and I would be too, that this is kind of overkill for this problem. But I'm trying to establish the procedure that we're going to use so that when the problem is a little more complex, you have some framework that you've already been exposed to. So we'll go ahead and break up these. We'll go through the formal process here, even though it'll be pretty easy in this problem. Well, if we look at vector 1 has no x component. It's all y component. And I'll just label the amount of y component f. Vector 2, it's also got no x component because it's all vertical. It's no horizontal. And then we've got a y component. We've got 50 pounds. And again, just like last time, I'm going to just deal with positive numbers here in my components. I'll deal with the directions when I do my sums. So there are our forces broken up into components. Our next step, if we were going to add these vectors together, like we did last week, we'd do a sum of x components and a sum of y components. Well, since these are forces now, we can change that labeling just a little bit. I would do it as sum of forces in the x direction and sum of forces in the y direction. Well, if we look at the sum of forces in the x direction, we've got x for vector 1 is 0. So that just goes in as 0. For vector 2, the x component's 0. So we get a whole lot of 0 there as our sum. In the y component, we get a little more interesting result. We've got f for our y component. It's unknown. If it had a number on it, we just write that number in, but we don't know how much force that is yet. So we're just going to label it as f. It's up, so it goes into the sum positive. Vector 2 has a y component of 50 pounds, but it's pulling down, so it's negative. And I really can't do any better with that. I really can't simplify that anymore. If you think about algebra, I've got an unknown and a number. I can't reduce that down. So if all we were going to do was form a sum of vectors, we'd be stuck right here. But we've got one more piece of information. We know this system is in equilibrium. And that tells us something very important. It tells us that these sums must be 0. The sum of forces in the x direction must be 0, and the sum of forces in the y direction must be 0. They have to be. If they weren't, then we'd have acceleration. If the sum of forces in the x direction here was not 0, then this thing would go shooting off in the x direction somewhere. If the sum of forces in the y direction was not 0, then it would go up or down. It would be moving. In equilibrium, the sum of forces must be 0. So we can say our sums have to be equal to 0. Now, of course, in the first one here, that doesn't buy us anything interesting because we had no components in the x direction. We can't have a sum in that x direction. So all the top equation does is tell us 0 equals 0, which is true, but not very enlightening. The bottom equation, the y direction equation, that gives us something we can solve. If I rewrite it over here, it says f minus 50 equals 0. We can solve that equation. And we can follow our steps for solving equations. I'm going to assume you're confident with solving equations at this point. You'd add 50 to both sides. And our force comes out to be 50. Don't forget that they are forces, so we'd label them in pounds. Now, you might have been able to guess that way back here or maybe even back here. But working through the procedure, we can see how the math will tell us that the force that the beam exerts on the object must be 50 pounds. So this is the basis of of all the problems we're going to solve throughout the first 2/3 of the class. All the equilibrium problems come down to basically this procedure. Draw a free body diagram and define a coordinate system. Break the forces up into components. Figure out your sum of forces in the x and the y direction. Set your sums equal to 0 because we're in equilibrium. Solve the resulting equations. That's the solution to an equilibrium problem. So let's do one here in the last bit that is a little more complex. Let's say we've got a situation that looks something like this. We've got a tug of war going on. And in this tug of war, we've got a person pulling to the left with 100 pounds of force. And we've got somebody pulling down with 30 pounds of force. And we want to find out how much force is a third person going to have to come in and apply, and what angle is that force going to make with some reference. So we'd have to draw that in here and try to figure out what would make sense. And generally, if you can draw it so it looks like it's physically going to be a tie, equilibrium you can think of essentially as a tug of war, no one's winning, where all the forces cancel out. In order to be in equilibrium, I'm going to have some force up here like this. It's going to definitely have to pull to the right to cancel out this guy, but it's going to have to pull up to cancel out this one. So I don't know how much force that is, so I'll just label it F. And I don't know what angle it's at. So right there, we have two unknowns. We have two unknowns that, so we know nothing about this third vector. We know everything about the 100-pound force. It's to the left, 100 pounds. We know its direction. We know its size. We know everything about this 30-pound force. We know nothing about this unknown force. That means there are two pieces of missing information. And that's the most we can handle in a problem like this. So let's see how we could solve this. Well, the first thing we'd want to do is define a coordinate system. And I'm going to choose my coordinate system basically to be my default. To the right is positive, to the is positive x, and up is positive y. We've already got a free body diagram here. In fact, in a lot of simple systems like tug of wars and things like that, the free body diagram basically falls out from the description of the problem. It's in more complex systems where we have to figure out the free body diagram from a more physical drawing. So we've already got our free body diagram here. So let's go to the next step. The next step is to break up the forces into their X and Y components. So I'm going to label my unknown force, force 1. I'm going to label the 30-pound force, force 2. And I'll label the 100-pound force, force 3. So let's go ahead and break those up. Now, I've got these three forces, force 1, force 2, and force 3. Let's deal with force 2 and force 3 first, since those are knowns. It's always easier to deal with your known forces before you deal with your unknown forces. So for an X component for vector 3, I've got 100 pounds. And again, I'll take care of the directions when I do my sums. I'm just going to deal with the positives here to avoid issues. Y has no Y component, so it's all X. Vector 2, I've got all Y component, no X. So no X component, but I've got 30 pounds of Y. And again, we'll take into account the sign, the direction, when we do our sum. And then we've got our unknown force. Now, last time we learned about how to use trig to get the components of that force. And your first instinct may be, certainly if you've been working on doing your vector addition homework, your first instinct would be to say, well, I've got this right triangle here. I've got a horizontal and I've got a vertical. I've got an adjacent and an opposite side. And it looks like my opposite side is Y and my adjacent side is X. So you might go through and say, well, X is going to be my unknown magnitude, F, times the cosine of my angle theta. And you might say, well, F sine theta will be my Y component. And that's correct. But it's not the most convenient way to do this problem. There are, the way we've got this set up, if we use our two unknowns together, we've created what we call a nonlinear equation. Whenever you multiply two unknowns together, it makes it a lot harder to solve the equations. So the better approach here, when you know nothing about the vector, when you don't know magnitude or direction, a better way to handle it is to treat as your unknowns the components and then build the magnitude and direction later on. So what I would do here is I would say, well, this horizontal piece, I don't know what it is. And rather than writing it as F cosine theta, I'm just going to write it as Fx, the X component of my force. And then same over here, I'm not going to write F sine theta. I'm going to write Fy. Remember that we can describe a vector in two different ways. We have that polar description in magnitude and direction, and we have the Cartesian description in X and Y component. Both are perfectly fine descriptions of a vector. So why not go with the one that makes it easier to deal with the problem? Use your X and Y component sizes as the unknowns. Then we can certainly, once we have numbers for these, we can go back and figure out from the Pythagorean theorem and inverse tangent, we can go and figure out the magnitude and direction, because we can't lose sight of what the problem's asking for. We have a specification here. We're asked for the magnitude and direction. That doesn't mean we have to use the magnitude and direction to solve the problem, but when we finish the problem, we better have a magnitude and direction. So whenever you know nothing, the biggest piece of advice I can give you about solving these kinds of problems is when you know nothing about the vector, don't use F cosine and F sine theta. Use Fx and Fy to figure out your unknown components. Then figure out, once you've got your answer, your magnitude and direction. A lot of problems will go a lot easier for you. Now, can it be solved with f sine theta and f cosine theta? Yeah, it can, but it's a lot harder and it requires some tricky algebra. It's a lot easier to just do it in 2 steps. Solve for your components and then figure out your unknown, the things you want, the magnitude and direction. So now that we've got this broken up, let's go ahead and do our sums. So we'll do our sum of forces in the x direction and our sum of forces in the y direction. And that just involves going down through each, just like we did with adding vectors, and taking into account direction. Well, fx here is the x component for my unknown vector, and that pulls to the right. So it goes into the sum positive. So I have positive fx. Vector 2 has no x component, so I don't need to bother writing anything. It's 0. Force 3 is all x component, but it pulls to the left. So it goes into the sum negative. So I have fx minus 100. That's my sum of forces in the x direction. If I had a number for fx, I would just subtract off 100 and that would give me my answer. But I don't have a number for that, so I have an unknown. I can't reduce this down to anything simpler. Do the same in the y direction. Since my unknown y pulls up, we'll just say fy positive. Vector 2, I have a y component that pulls down, so that'd be minus 30. And vector 3, no y component, so nothing better to do there. So our next step is to recognize that this system is in equilibrium. So this is where it's different from just taking a vector sum. We have to realize we know what that sum needs to be. The sum has to be 0. If this is in equilibrium, which is what we want it to be in equilibrium, then the sums must be 0. That gives us 2 equations we can solve. Fx minus 100 equals 0, and Fy minus 30 equals 0. Now, both of those are relatively straightforward equations to solve, and hopefully it's not too difficult for you to see that Fx then must be 100 pounds, and Fy must be 30 pounds. And that kind of makes sense physically if you look at the free body diagram. Remember that being in equilibrium is all about the forces canceling out. So since we have 100 pounds to the left, something's got to pull to the right with 100 pounds. We've got 30 pounds down, so something's got to pull up with 30 pounds. And since we only have one unknown force, that's got to be it. It must pull to the right with 100 pounds of force and pull up with 30 pounds of force. So we've almost solved the problem. The only piece that's missing is we have to figure out our magnitude and direction. And that we can do with our Pythagorean theorem and inverse tangent. We've got a right triangle here. So if I blow this up a little bit, we've got fx. And I would draw it just like this. I would draw it fx to the right, and that is 100 pounds. Then at the tail of that, or at the head of fx, I would draw fy. Since in our drawing up here, we want the angle to horizontal. Remember, we always want our components to enclose the angle we want. So that's going to be 30 pounds. And then my resultant has a magnitude f and an angle theta. Well, we can find the magnitude from the Pythagorean theorem. It's going to be the square root of the side squared. So we'd have 30 squared plus 100 squared. And we can go over to our calculator and figure out what that is. We take 30 squared and 100 squared and add those together. Take the square root. we get 104.40. And I'm keeping 5 significant figures here somewhat arbitrarily. I'm going to assume that this problem told me to write my answers to 3 significant figures. So this is an important idea, and something that could become important to you for other things, including the quiz that we have out. So they want f and theta to 3 sig figs. So f and theta to 3 sig figs. I'm assuming that's told to us in the problem. Good practice to get into is that when you know you have a target number of significant figures that you want in your problem, that you want to have good in your final answer, keep 2 more throughout the problem. So anywhere you round until you get to your final answer, keep 2 more sig figs than what you want. So here I want 3 good sig figs in the end, so I'm going to keep 5. So I'm not done. I haven't written my final answers yet. These are all intermediate values. Until I go to write my final answers, I'm going to keep 5 sig figs, and then I'll round off those last 2. Here it doesn't make a big difference, but in other problems where we'll have sines and cosines that will be rounding off, if you round off all your sines and cosines to 3 sig figs, you're not going to have 3 good sig figs in your final answer. Round off error will take you out of tolerance pretty quickly. Keep 2 more sig figs than what you need in your final answer, and only round to that final number of sig figs when you are writing down your final answers. So that gives us our magnitude. Then we need our direction. The angle is the inverse tangent of the opposite over the adjacent, so 30 over 100. So our inverse tangent looks like 16.699 degrees. So there we have our numbers. We can go off to the side now or back to our answer sheet or wherever we're going to formally put our final answers, and we can say force is, to round that down to 3 sig figs, 104 pounds. Don't forget the units. And the angle rounded to 3 sig figs, that would be 16.7 degrees. You should always be rounding to your final number of sig figs, only be rounding to your final number of sig figs in that last step where you're presenting your answers. That's what that final number of sig figs is all about. Use 2 more everywhere else in the calculation, and you'll never have round off error be a problem. So that is the basic idea behind an equilibrium problem. In our practicum session this evening, we'll look at a box on a wire, which is a little bit different, similar idea, but has some other complexities with it. But this will help us out quite a bit, being able to split the force up into components. We'll do another version of this that I have to help you out with a few other quirks that kind of come up in realistic problems. So some important problems coming up here in our practicum session. So let's finish up the class here. Next time, strictly practice on these types of problems. So that'll be the topic for our 3rd homework assignment. And so, but there's not much in the way of lecture notes for next time. For Wednesday, it's just going to be working on problems. I'll do a few more example problems. I'm sure there's going to be a question or 2 off the homework. So we'll be taking a look at that also. And then, and we'll be finishing up with concurrent problems. Anyone have any questions? All right. So same as last week, we'll be taking about a 10-minute break. If you're hanging around for the practicum session, we'll be back at in 10 minutes. And if you're heading out, have a good evening, and I'll see you on Wednesday night.